Hey everyone, welcome back to my YouTube channel, Our Solar System. We think we know it. A grand, familiar neighborhood of planets, moons, and asteroids, all orbiting our star. For centuries, our telescopes peered outwards, mapping, categorizing, and slowly, painstakingly, building a picture of our cosmic home. But what if I told you that beneath the familiar surfaces of some of these worlds, hidden from our gaze, lie secrets so profound they could redefine our understanding of life itself? What if, in our very own cosmic backyard, there exist entire oceans, vast and deep, holding more water than all of Earth's oceans combined, yet completely invisible from the surface? This isn't science fiction. This is the staggering reality unfolding right now, a cosmic mystery that demands an answer. How can we have worlds teeming with liquid water, potentially harboring conditions ripe for life, right under our noses, cloaked in miles of ice? This paradox, this impossible question, is what drives one of the most thrilling quests in modern astronomy. It challenges everything we thought we knew about habitability, about where life can thrive, and about our place in the universe. We are on the verge of incredible revelations, discoveries that could fundamentally alter our perspective. The answers lie in the hidden depths, in the silent, dark waters of worlds we are only just beginning to understand. Imagine the implications. Imagine the sheer wonder. But before we dive into the breathtaking possibilities, before I reveal the most astonishing details of these hidden realms, you need to understand the journey of discovery itself. The story of how humanity first glimpsed these veiled oceans is a testament to perseverance, scientific ingenuity, and a relentless curiosity that pushes us to explore the unknown. It's a story filled with twists, turns, and moments that left scientists scratching their heads in disbelief. But to understand this cosmic mystery, we need to go back to where it all began, to the first whispers of water in the cold, dark reaches of space. The year was 1979. NASA's Voyager 1 and 2 spacecraft were on their grand tour of the outer solar system, sending back humanity's first close-up images of Jupiter and its retinue of moons. Among them was Europa, one of Jupiter's 4 largest moons. What Voyager saw was utterly baffling. Europa wasn't the cratered, dead world many expected. Instead, its surface was incredibly smooth, almost devoid of large impact craters, but crisscrossed by an intricate network of long, dark lines resembling cracks in an eggshell. This was a stark contrast to its heavily cratered neighbor, Callisto, or the volcanically active Io. Scientists pored over these images, trying to make sense of the fractured terrain. The leading theory at the time suggested a thick ice crust, but the patterns of the cracks were unlike anything seen before. There were suggestions of plate tectonics, similar to Earth's, but on an icy world. It was a tantalizing hint, a whisper of something dynamic beneath the surface, but definitive proof remained elusive. The data was sparse, the resolution limited, and the true nature of Europa remained a profound enigma. Then came the Galileo mission. Launched in 1989, Galileo spent 8 years orbiting Jupiter, making repeated flybys of its moons. This was our chance to get a much closer look, to truly unravel the secrets hinted at by Voyager. As Galileo swooped past Europa, its instruments began to pick up peculiar readings. The moon exhibited an induced magnetic field, a phenomenon that suggested the presence of a subsurface layer of electrically conductive material. What could be conductive on an icy moon? Salty water. This was a monumental breakthrough. The magnetic field data provided the strongest evidence, yet that Europa harbored a vast, salty ocean beneath its icy shell. Imagine the excitement, the frantic analysis, as scientists grappled with this paradigm-shifting discovery. But even with this powerful evidence, the direct observation of liquid water remained a challenge. How could a world so far from the sun maintain a liquid ocean? The answer lay in a phenomenon called tidal heating. Jupiter's immense gravitational pull constantly stretches and squeezes Europa as it orbits. This continuous flexing generates friction deep within the moon, producing enough heat to keep a vast ocean from freezing solid. It was a brilliant solution to the energy paradox, but it still felt almost too good to be true. A hidden ocean, warmed by the gravitational embrace of its giant parent planet. But the story didn't end with Europa. Just as scientists were coming to grips with the implications of a subsurface ocean on one Jovian moon, another discovery, far more dramatic and unexpected, was about to unfold at Saturn. This time, the revelation would come not from indirect magnetic readings, but from a direct, undeniable spectacle of cosmic geology. The investigation deepened dramatically with the arrival of the Cassini-Huygens mission at Saturn in 2004. Cassini was a technological marvel, designed to study Saturn and its rings and moons in unprecedented detail. Among Saturn's icy satellites, one stood out as particularly enigmatic: Enceladus. Earlier Voyager flybys had shown Enceladus to be a small, bright world, but with an unusually smooth, uncratered southern hemisphere, suggesting recent geological activity. This was already intriguing, but nothing could prepare scientists for what Cassini was about to reveal. In 2005, during a close flyby, Cassini's instruments detected an astonishing phenomenon. Massive plumes of water vapor and ice particles erupting from the moon's south pole, shooting hundreds of kilometers into space. Imagine the sheer disbelief and excitement in mission control. It was like witnessing a cosmic geyser, a direct window into the interior of an alien world. This wasn't just evidence, it was a smoking gun. The plumes were clear, undeniable proof of liquid water beneath Enceladus's icy crust. But here's where it gets even weirder. Cassini didn't just see the plumes, it flew right through them, sampling the ejected material directly. The analysis of these samples was revolutionary. They contained not just water vapor and ice grains, but also salts, silica nanoparticles, and organic molecules. The presence of salts strongly suggested that the plumes were originating from a subsurface ocean in contact with a rocky core, where water-rock interactions could be occurring. This is crucial because on Earth, such hydrothermal activity at seafloor vents provides energy and nutrients that support entire ecosystems, completely independent of sunlight. Silica nanoparticles were particularly compelling. They form when hot water interacts with rock, indicating active hydrothermal vents on Enceladus's seafloor, much like the black smokers found in Earth's deep oceans. This was a profound plot twist in our understanding of habitability. It wasn't just about liquid water. It was about the right kind of liquid water, with the right chemistry, the right energy sources. The sheer volume of water detected was staggering. Scientists calculated that Enceladus harbors a global ocean beneath its south pole, and later studies confirmed it to be a global ocean beneath the entire crust, warmed by tidal heating from Saturn's gravity. The moon, barely 500 kilometers in diameter, less than a tenth the size of Earth, held an ocean that could potentially rival Earth's in its potential for life. This was a game-changer. It expanded our definition of a potentially habitable world far beyond what anyone had previously imagined. It wasn't just Europa anymore. Enceladus, a tiny, unassuming moon, was screaming out a message of potential life. But the revelations didn't stop there. As our understanding of these icy worlds grew, scientists began to re-examine other moons. What about Ganymede, Jupiter's largest moon, even bigger than the planet Mercury? Data from Galileo hinted at a subsurface ocean there too, potentially sandwiched between multiple layers of ice. And Callisto, another of Jupiter's Galilean moons, also showed signs of a buried ocean. Even Neptune's moon Triton, a captured Kuiper belt object with its geysers of nitrogen, is suspected of harboring a subsurface ocean. This wasn't just a few isolated cases, it was becoming a pattern. Our solar system, once thought to be a relatively dry place beyond the Earth, was turning out to be a cosmic water park, with vast, hidden oceans tucked away inside numerous icy bodies. Each new piece of evidence, each new detection, built upon the last, painting a picture of a solar system far more dynamic, far more mysterious, and potentially far more alive than we had ever dared to dream. The sheer audacity of these hidden worlds, existing in the cold, dark depths, powered by gravitational tugs, and potentially brewing the ingredients for life, is a testament to the universe's boundless creativity. But the biggest revelation, the one that truly captivates our imagination, still awaited confirmation, the ultimate question of life itself. This brings us to the modern quest, a scientific battle fought with cutting-edge technology and brilliant minds. The tantalizing hints from Voyager, Galileo, and Cassini have ignited a new era of exploration. We are no longer just guessing. We are actively designing missions to seek out and characterize these hidden oceans, to answer the ultimate question. Are they truly habitable, and could they harbor life? The star of this new era is undoubtedly NASA's Europa Clipper mission. Scheduled to launch in 2024, Europa Clipper will make nearly 50 close flybys of Europa, dipping as low as 25 kilometers above the moon's surface. Its suite of sophisticated instruments includes cameras, spectrometers, a magnetometer, and even an ice-penetrating radar. This radar, called Reason, will be able to probe beneath Europa's icy shell, searching for liquid water, and even attempting to characterize the thickness of the ice and the depth of the ocean. Imagine the data this mission will send back. Imagine the images, the detailed chemical analyses. We are talking about getting closer than ever before, almost touching the surface of this enigmatic world. But Europa Clipper isn't alone in this grand endeavor. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE mission, launched in April 2023, is also on its way to Jupiter. While JUICE will focus primarily on Ganymede, it will also conduct flybys of Europa and Callisto, providing complementary data and adding to our understanding of the Jovian system's ocean worlds. These missions represent humanity's most ambitious attempt yet to unravel the secrets of these hidden oceans. Scientists are locked in a fascinating debate, a scientific battle of theories. What are the precise energy sources driving these systems? How much organic material is truly present? Are the conditions stable enough for life to emerge and thrive over billions of years? The conflicting theories revolve around the exact composition of the oceans, the nature of the water-rock interactions, and the long-term stability of these subsurface environments. Some scientists believe that the tidal heating on Europa is so intense that it could create a dynamic, chemically rich environment perfect for life. Others are more cautious, pointing to the immense challenges of life existing without direct sunlight. Recent discoveries continue to challenge our understanding. Reanalysis of old Hubble Space Telescope data, for example, has shown potential evidence of water vapor plumes erupting from Europa's surface, similar to Enceladus. If confirmed by Europa Clipper, this would provide an even more direct way to sample Europa's ocean without having to drill through miles of ice. Imagine a future where a probe, perhaps a future lander, could descend into one of these plumes, directly tasting the ocean's chemistry. This is the climactic revelation we are building towards, the direct observation of the conditions for life, perhaps even the detection of biosignatures themselves. The very thought sends shivers down the spine. We are on the precipice of potentially finding alien life, not light years away in distant exoplanets, but right here, in our own solar system, in the silent, dark waters of these hidden worlds. The next decade promises to be a period of unprecedented discovery, a time when our understanding of life's potential homes could be completely rewritten. The implications of discovering life in these hidden oceans are nothing short of monumental. It would fundamentally change our understanding of biology, of habitability, and of our place in the cosmos. If life can arise and thrive in environments so different from Earth's, deep beneath miles of ice, warmed by tidal forces, then the universe must be teeming with life. It would mean that the conditions for life